Kepler's laws. Kepler's law inform us, tell us about the laws that govern, that rule the motion, planet's motion in the solar system. There are three Kepler's laws. The first Kepler's law, says that all the planets in the solar system move in an ellipsis around the Sun, and the Sun is located in one of the focal points of this ellipsis. Here is an example, a picture that shows how it looks like. We have here, this line is an ellipsis. Such an ellipsis can be characterized by a semi-major axis, which is the half of the major axis. Here, from this point to this point, is the major axis. Half of this, from this point to the center, or from the center to this point, is the semi-major axis. So according to this picture, the major axis is marked with 2a, therefore semi-major axis will be a. Another feature or characteristic is semi-minor axis. If so, we speak also, of course, about minor axis. Minor axis is the line from this point to this point, and is marked by 2b. So the semi-minor axis is b over here. Also, we can find, speaking about the ellipsis, two focal points, or two focuses. The first one and the second one, marked with the letter F, capital letter F. And according to the first Kepler's law, the Sun is located in one of their two focal points. In our picture, the Sun is located on the left, the yellow small dot. This is the Sun. So any planet, of all planets in the solar system, move along this ellipsis. And the Sun is located in one of the focal points, either here or here. Okay? And here's the definition of the first Kepler's law. Planets move in elliptical orbits with the Sun at one of the focal points. That was the first Kepler's law. Now the second. Again, we have the same ellipsis, or analogical ellipsis, like this. The Sun is located in one of their focal points. A planet, a given planet, is moving in this ellipsis. Say that the planet initially is in this point, and after a certain time, delta t, the planet is over here in this point. The initial position of the planet can be represented by this line that connects the Sun and the planet. You can call it, if you prefer, the radius of the ellipsis. The final position of the planet is over here, and also there is a line that connects the Sun and the planet. The two radii, as in this one, sweep out a certain area which is marked here with P2 within the time delta t. Okay, this area between the two lines, the two radii, and this arc. All this inside is the area which is swept out by the radius of this ellipsis. Now take into account another position for the same planet over here. This is a starting position, beginning position, and the final position, terminal position, is over here. And again, if we assume that the time of the planet's movement, planet's motion, is still the same as previously, delta t, and the radius, or the line that connects the Sun with the planet, this line sweeps out a certain area, P1. Okay, all is inside the two radii, the two lines that connect the Sun and the planet. The initial position of the planet, the final and terminal position of the planet. Between the two lines and the arc, there is an area which is marked here with P1. It turns out that the two areas, P1 and P2, are the same, provided that the time of observation is the same, and in our case equals delta t. Okay. It may seem that the two areas have different shape, which is true. P2 and P1 areas have different shapes, but the value, the magnitude, in terms of how much is the same. And this is the second Kepler's law, which says that a line from the Sun to a planet sweeps out equal areas and equal lengths of time. Okay? Below we have two equations, but the two equations say exactly the same what I said a while ago, but in a little bit different form. The orbital moment of momentum, which is marked here with the letter, capital letter L, is equal the mass of the planet times the radius of the line that connects the planet with the Sun times the velocity of this planet. And it turns out that the orbital moment of momentum is constant. Okay, if you multiply here the sign, this multiplication sign, or you can associate it with the letter x. This is not x, this is a multiplication sign. A multiplication, vectorial multiplication of their radius and the velocity. If you multiply the two quantities in a vectorial form, then you'll get a certain number which will be again a vector, and this vector multiplied by the mass gives all the time the same number. Therefore, the orbital moment of momentum is constant. the radius known or understand as a vector, and the velocity understands as a vector change. For example, if the planet is over here, the radius is like this, and the velocity is, say, v prime. The radius, r prime velocity, v prime. Now, the final position of the planet is over here. The radius has changed, now has a different length, and the velocity has a different value. The tangential velocity, we are speaking about the tangential velocity. But again, the change of the radius and the velocity has such a value that is comparable in terms, is equal to the initial radius multiplied by the initial velocity of this planet. So whatever time you take, the orbital moment of momentum is the same, doesn't change, is constant. And the below formula that the area's velocity, which is the change of the area divided by the change of the time, this velocity says us that the areas, the change of the areas within the same time is constant. This is what was said a while ago. But again, for students who are not too much familiar with mathematical calculations, these two formulas, these two equations, you are not needed to remember them. The only thing you need to memorize is this definition, is this text or description of the second Kepler law. Now the third Kepler law. Over here, say, is that, and this black ball or black dot represents a certain body, for example, a satellite that is moving around there, approximately in a circle. But if we convert this ball, which is initially our head, and replace it to the sun, this ball is replaced to any planet in the solar system, and this line, as you already know, is not a circle but an ellipsis. So let's imagine here is the sun, here is a planet, no matter which one, and there is a gravitational force between the sun and the planet. The gravitational force is equal gmm divided by r squared. This is the interaction force or force of attraction between the two bodies, between the two objects. M stands for the mass of the sun, capital letter M. Lowercase letter m stands for the mass of the planet. R is the distance between the sun and the planet. G stands for the gravitational constant. You should know it from the gravitational field discussion. This force is the attractive force, therefore the planet is being attracted by the sun. Therefore, this vector is directed to the sun. Because this planet is moving in an ellipsis, then there is a certain force of inertia, known as the centrifugal force, which is equal mv squared divided by r, m the mass of the planet, v the tangential velocity of this planet, r is the distance between the planet and the sun. The centrifugal force, or the force of inertia, is directed exactly oppositely to the force of the gravitational force. Okay, but because this planet is stable in its orbit, therefore we have to conclude that the two forces, the gravitational force and the centrifugal force, must be equal. And we are going to use it to calculate some quantities and their relationship. I mean, first of all, the period of this motion and the radius, or if we are speaking about the ellipses, which is the case, then instead of radius, we have the semi-major axis. But starting from what was said, the gravitational force is equal to the force of inertia, or the centrifugal force. This is that equation. Gmm divided by r squared is equal mv squared divided by r. This is the same what is over here. Okay? And we are driving up to get a certain interrelation between the radius, or more precisely speaking, between the semi-major axis and the period in this motion. I would like to remind you that the period is the time of the 1/4 cycle of the planet around the sun, if we are speaking about this situation. So we are here now, and from the circular motion, we know that the velocity, the tangential velocity in the circular motion is 2 pi r divided by t. T stands for the period. Let's take it and substitute v over here. Prior to this, let's cancel out a lowercase letter m and 1 r over here and over here. Okay, so upon substituting v with this term, the right-hand side of this equation, 2 pi r divided by t, you'll get the right-hand side of the original equation written like this. Okay, left-hand side, sorry, not right-hand side, left-hand side. And the right-hand side, after cancellation, is given like this. Okay, now let's rearrange this equation so that to get the radius and the period on the left-hand side and the rest on the right-hand side. If you do so, based on some mathematical operations, very simple operations, you get this formula in the bold letters. R to the cube divided by t squared is equal to gm divided by 4 pi squared. On the left-hand side, we have the radius and the period. On the right-hand side, we have g, which is constant, the mass of the sun, which is constant, 4 pi squared, is also constant. Therefore, we can conclude that the left-hand side, there is a ratio, the radius to the cube divided by the period squared is constant, doesn't change. Because we know that the planets move in an ellipsis according to the first Kepler's law, therefore, instead of letter R, which stands for the radius, we can use the letter A, which stands for the semi-major axis. And in order to get this formula complete for without any errors, without any faults, we need to take into account also the mass of the planet. Therefore, on the left-hand side, we have a to the cube divided by t squared, and on the right-hand side, we have the mass of the sun plus the mass of the planet, uppercase letter m plus lowercase letter m. And this is what the third Kepler's law says, that the semi-major axis raised to the cube divided by the period squared is constant, because all the terms on the right-hand side is constant. G is the gravitational constant. Uppercase letter m is the mass of the sun is constant. Lowercase letter m is the mass of the planet is constant. Of course, the denominator 4 pi squared is also constant. We can write it as like this. Instead of constant, we can use, for example, any letter. In our case, the letter K has been used. Okay, so this is a simplified form of the third Kepler's law, or a little more expanded is this one. Okay, so again, the third Kepler's law says that the ratio of the semi-major axis raised to the cube to the period of the planet's cycle squared is constant. And this is what you should know along with either this or this formula, provided that you understand that the letter K is a simplification for the right-hand side of this equation, G times uppercase letter m plus lowercase letter m divided by 4 pi squared. Okay, so those were the 3 Kepler's laws. Now let's do an example which is titled Distance from the Sun to a Planet. And according to what you see over here, we have a Jupiter, and the period of the Jupiter is 11.86 years, and we need to find the radius, or more precisely speaking, the semi-major axis of the Jupiter in its revolution around the Sun. If so, if we are speaking about the axis, semi-major axis, then the first thought which comes to our mind is to apply the third Kepler's law, because the third Kepler's law contains the semi-major axis and the period. Okay, As it was said, no matter what planet we take into account, the ratio of the semi-major axis raised to the cube divided by the period squared is constant, doesn't change. So it means that if we take, for example, the F and make this ratio, and next we'll take, for example, Jupiter and make this ratio, it turns out that the two ratios are the same, according to the third Kepler's law. Therefore, the first ratio, for example, for the Jupiter, must be equal to the ratio for the F. Okay? Let's assume that the radius or the semi-major axis for the F is 1 astronomical unit. And the time of the full revolution or the full cycle of the Earth around the Sun is 1 year. Therefore, over here we have 1 raised to the cube divided by 1 raised to the second power. Of course, the right-hand side is equal to 1. Therefore, after rearrangement, we'll get that r raised to the cube is equal t raised to the second power. If we extract the cube root for both sides, we get this equation that r, which stands for the Jupiter's semi-major axis, is equal to the cube root of t squared, where t is 11.86 years. So we have solved this problem using letters or symbols, and the last step is to insert numbers, which is not much important. The most important is to understand, as usual, you need to understand how to solve a given problem, and substituting or plugging in numbers is the last step, and all of you can do it using any calculator. So summarizing again, the three Kepler's law have been discussed, and they sound like this. The first Kepler's law, a planet moves in an elliptical orbit with the Sun at one of the focal points. Second law, a line from the Sun to a planet sweeps out equal areas in equal length of time. The third Kepler's law, the ratio of the semi-major axis raised to the cube to the period of the planet's cycle squared is constant. Okay. And now one more problem. Determine the height of a geosynchronous satellite. Given that we know the mass of the Earth, is 6 times 10 to the 24 kilograms. The situation looks like this. Here is the Earth, this big ball, and here is the position of the satellite. Uppercase letter R stands for the Earth radius, H stands for the height above the Earth surface if we are speaking about the satellite, for the satellite, and lowercase letter r is the sum of the Earth radius and the height of the satellite. So I would like to emphasize, and I would like to sensitize you to understand what are our given and what we are looking for. Determine the height. It means that we are looking for this h. Okay. Simultaneously, keeping in mind that the h can be found as the lowercase letter r minus the uppercase letter r. We are going to use it at the end, but let's start from finding the radius, which the lowercase letter r, which is into this picture, the sum of the uppercase letter r and the height of the satellite h. In order to do so, we need to equalize the centrifugal force and the force of gravitational force, because the two forces are the same. If we have a certain body which is moving in a circle like this around the Earth, and the gravitational force which is acting on this body, on this satellite, is nothing but a centrifugal force, Fc. Centrifugal force is the force about which we know from the circular motion. So again, centrifugal force is equal to gravitational force. Centrifugal force can be found according to this equation, according to this term, this expression, mv squared divided by r. This equation is this term is exactly the same as for the centrifugal force, of which we have already spoken. Equals, and the right hand side, gmm divided by r squared. This is the gravitational force. So again, we are looking for r, so we need to make some mathematical conversions, perform some mathematical operations. First of all, we need to apply this formula for velocity, for the circular velocity, 2 pi r divided by t. This formula is taken from the circular motion again, and plug it in for v. Okay. Then what is possible? Cancel out, and what remains is written over here. Okay. Now let's raise to the second power numerator and denominator and cross multiply. The resultant figure is given over here. Then divide by 2 pi both sides. We have this form then. Then extract the cube root from both sides, which gives us the radius r, or the distance rather, which is the sum of the Earth radius and the height at which the satellite is located. So the final formula for r, lowercase letter r, is this. Now, because we are looking for the h, not r, not lowercase letter r, according to this picture, again, h is equal lowercase letter r minus uppercase letter R, which is written over here. So the final step, it would be to take right-hand side of this equation and substitute lowercase letter r over here. By this means, you get your unknown h, which is the height at which the satellite is located above the Earth surface. And one more problem. Determine the acceleration due to gravity, the period and the speed at the space station 275 kilometers above the surface of the Earth. So again, we know the map of the Earth can be found either in a textbook or in a table or on the internet if you prefer. We know the radius of the Earth, which is given over here, 6.4 times 10 to the 6 meters. The text is again over here, and our data given here. In order to find the acceleration due to gravity, we need to apply this formula. The left-hand side stands for the weight of this space station, and g stands for the gravitational acceleration, or in our case, so-called terrestrial acceleration. Right-hand side is the force, the gravitational force, of which we've already spoken. The two terms, left and right, are equal because they represent the same quantity, force, or roughly speaking, approximately the weight. After rearrangement, you can find g. At first cancel lowercase letter m, then g equals lowercase letter g equals uppercase letter g times mass of the Earth divided by r squared, where r is the radius of the plus a certain height, this height above the Earth surface. In order to find the period, we are using this formula or this equation. Left-hand side stands for the gravitational force, and the right-hand side stands for the centripetal force. But the only difference is that instead of v, we have 2 pi r divided by t. We are taking this one instead of v, and then after plugging in to the centripetal force formula, we'll get this form. After conversion, we can find t, the period. Okay. In order to find the velocity or the speed, if you prefer, we are using the circular motion formula for the tangential velocity, which is 2 pi r divided by t. Okay, t has been already found above, r is known. What is, by the way, what is the difference between velocity and the speed? Because I have used it interchangeably, but you need to know that there is a certain difference between the two. Speed is so-called scalar. In other words, is a pure number. Velocity is not only a number, it's not only a magnitude, but it has some other features because velocity is a vector, not a scalar. If velocity is a vector, then it has not only the magnitude but also direction and distance. Direction is the line on which this vector lies, and distance is marked or is graphically represented by the arrow path of this vector. So this is what you need to know if we consider the three Kepler's laws and some examples, some sample problems in terms how to solve them. I emphasize once more that at first, the first approach for problem solving is to read attentively the text and write down your data in a node, your given and your unknown, then write down a formula, an equation, which can potentially enable us to solve for our unknown, then convert this formula, this equation, in order to find the unknown. Not until then, you may insert plug-in numbers.